Hey, what's up everyone? Welcome to Descriptive Chem / Lab Part 4. Today we're going to go over volumetric glassware, titrations, and redox reactions. So let's determine what a volumetric glassware is. A volumetric glassware is glassware inscribed with markings to help measure the volume of a liquid. And you're going to have two different types of volumetric glassware. First of all, it's going to be TC versus TD. TC is going to be to contain at 20 degrees Celsius, and then TD is going to be to deliver at 20 degrees Celsius. Sometimes you might see them labeled as in, and then X for deliver. And so what do these mean? Well, to contain is designed to hold exactly the amount listed. And so when you have a liquid in a container and you dispense that liquid, well, some of the liquid is going to stick to the sides of the wall or whatever. And so whatever amount that you really contain isn't the amount that you dispense. So contain is just to contain it, but if you were to dispense it, you would actually get less than the amount that you are actually containing. Deliver does the opposite. So it actually holds more than the volume listed, but if you were to dispense it, so let's say you had a 50 ml to dispense, you would dispel 50 mils, but you would probably have more than 50 mils in the container itself. So again, to contain, it holds the volume. To deliver, it delivers, it dispenses that exact volume. And so let's learn how to read volumetric glassware. You might have learned what a meniscus is, and you might have learned that it's just like the lowest point of that little curve or whatever, but it's not really the lowest point. It's the point that's going to be symmetrical with the middle point. So if you look at straight down the middle of this container, you're going to get to the meniscus. And so depending on what type of liquid you're going to hold, some curves might be concave and some might be convex. I think that's like the formal name, but I mean it just means like a open parabola or like a down parabola. So you have to look at down the center to find the meniscus. You can't just look at the lowest point. You also need to be eye level with the meniscus so you can read it the most accurately. But yeah. All right, let's get some practice reading menisci. I don't know. So the rule with meniscuses is that you're allowed to account for one more significant digit than you can know for sure. So in this one, we know for sure that it's going to be 3.8 because we know that that little marking right there tells us an 8. But we're allowed to account for one more digit. And so I think that looks like 3.81. So I'm allowed to do that. I'm allowed to add one more digit than I know for certain. And in this one, it's a bit less clear why you would do that. But let's take a look at this one. Right? So in this one, we know for a fact it's going to be, that's like a 6. So we know that it's going to be at least 2.6, sorry. But I'm allowed to make one more digit after that. And I think that looks like 2.65. So I'm going to write 2.65, and I'm allowed to do that. What you're not allowed to do is, write another digit. Like I think that looks like 2.652. You are not allowed to make another digit. You can only make one digit past what you're certain about. So let's get some practice reading them in actual problems. And the difference between this problem and what we just did is that we're using a buret. And so in the meniscus that we were using before, or the container that we were using before, the numbers go up from bottom to top. But in a buret, the numbers go up top to bottom. And we'll see why this is important. But basically, you read them the same way. In the other one, we were reading them from from bottom to top. This one, we're going to read from top to bottom. A student is using a buret for a titration. What is the initial buret reading that should be recorded? So we know that it's going to be at least 6.6. We know that for certain because of this little marking right here. That's 6.6. But again, we're allowed to make one more significant number value. So I think that it's going to look like 6.63. And I'm allowed to do that. So the answer is going to be C. And the trick answer here would have been A, right? 6.6. But again, you're allowed to make one more than you know for certain. And so the answer is going to be C. And we're correct. All right, let's take a look at one more. So what is the reading of the buret shown? Again, we have a buret. And in this one, we know for certain that it's going to be at least 30.3. Remember, 1, 2, 3. So 30.3. But again, I'm allowed to make one more than shown. And so I think that that looks like 30.30, right? That looks right on the 3 mark. And so the answer that I want to go with is C, which is 30.30. And that is the right answer. So again, you're allowed to make an estimate that is one significant value larger than what you know for certain. And let's move on. So we're going to have 4 different types of volumetric glassware. And you might see that there's 6. 5 and 6 are not volumetric glassware. I want to make that clear. Beakers and erlenmeyer flasks are not volumetric glassware. And the reason I put them here is so that we can see why they're not. So again, the only volumetric glassware are going to be these. And I think there are more. Like obviously there are going to be more volumetric glassware. But the ones you got to know about are 1, 2, 3, 4. I just realized it says volumetric gasware. Okay, my bad. Anyways, let's take a look at graduated cylinders. So graduating cylinders look like this. They measure with an error of 0.5% to 1%. So the whole theme around volumetric glassware is that they're going to be super accurate. And we'll see that's why 5 and 6 are not volumetric glassware, because they are not as accurate as some of these. Also, in all of these volumetric glassware, I don't know if you can see it, but it's right here. So when you go to buy volumetric glassware, it's going to show you whether or not it's going to be to deliver or to contain. So in this one, we have X, which means it's going to be to deliver. But in this one, we're going to have an IN right here. I don't know if you can see it, but that means that's to contain. So again, these are in like actual things you can buy, and depending on what you need it for, you might buy a graduated cylinder to contain a liquid, or you might buy it to deliver a liquid. So again, just try to get familiar with this picture. A graduated cylinder is going to look like this. A volumetric flask are going to be like those big weird flasks, and they're usually used to prepare big solutions of known concentration. And they actually have a massive range of sizes. So you see like I think that looks like a 2-liter one right here. And you might, I don't know what this is. But really they go from anywhere between like 1 milliliter to 2 liters. It's crazy. And their error percentage is really low. It's an error of about 0.1%. And the thing with volumetric flasks is that they don't have those little markings on the side that increment in volume. Rather, you're going to have a marking on the top here that tells you what the total what the total volume is going to be. So again, just get comfortable with knowing that a volumetric flask looks like these flasks right here, and you'll be fine. Let's move on to burets. So burets do not actually hold the volume indicated. So right here, the incrementation for a buret starts way at the top, right, and then it works its way down. But you might notice that the last increment is right here. But it contains all this amount more. And so burets are not actually designed to hold the volume indicated. They're used to accurately dispense a known amount of liquid. So really, we're caring about the change in liquid level rather than the actual reading. So in a buret, we're usually using it for a titration, and we'll look into what titrations are. But what you're looking for is the initial reading and the final reading, and you would subtract these values to find the amount of volume that has been dispensed. And so these burets are super accurate, and they're super helpful for certain things, but they are not very helpful in, holding a certain amount of volume. All right, last one, we're going to have pipettes. So pipettes are designed to hold a single specific volume, and they're generally going to be used for small volumes from 1 mil to like 100 mils. And you can see there's like little marks over here. These basically hold up to a certain amount, and then you can dispense them. I'm pretty sure you've used a pipette before. You know how they work, but they look like this. And so let's move on to beakers and erlenmeyer flasks. They are not volumetric glassware, and the reason why is that they're only used for crude volume estimations. They have an error of about 5%, and that might not sound like a lot, but that's more than enough to disqualify them as volumetric glassware. Again, they're just used for like crude estimations. You should not be using these if you need specific, accurate measurements. Also, a beaker looks like this, and an erlenmeyer flask looks like this. So I guess just get familiar with just knowing what they look like. Let's move on to some problems. Which 50 ml container would be most suitable for measuring and dispensing 37 ml of an aqueous solution? Well, we know that the Erlenmeyer flask and the beaker cannot be it because they are not volumetric glassware. They are quite inaccurate, and you should not be using them for accurate, like precision stuff. Also, this is like a burette here. This is like a different type of burette. You should not be using a burette because you can't really measure 37 mils. You can only measure like a change in that. So you should not be using B. Rather, you should be using D here, which is a graduated cylinder. And a graduated cylinder will allow you to, measure 37 mils and then dispense it with pretty high accuracy. And we are correct. Let's move on. Which would be the most suitable for measuring 2.7 mils of ethanol for addition to a reaction with acidified dichromate? That whole reaction stuff is irrelevant. We're basically looking at 2.7 mils of ethanol. What would we use to measure that? Well, we can get rid of beaker here because, again, it's not volumetric. We cannot be super accurate with that. The next thing we can get rid of is going to be a volumetric flask. Remember, volumetric flasks only have a certain like marking, and so a 10 mil volumetric pipette is only going to have a 10 mil marking. So you don't know when 2.7 mils are going to be filled up. The only thing you know is whether or not 10 mils have been filled up. And it's kind of the same story with the volumetric pipette. Again, you're going to have a specific marking, and you won't know whether or not you have 2.7 or 2.8 or 2.9. You just don't know. You can only estimate. But the one thing that you can do is in a 10 mil graduated cylinder. In a 10 mil graduated cylinder, you're going to have those, tenth decimal markings. So you're going to have, 0.1, 0.2, etc. And you should be able to measure 2.7 mils of ethanol with pretty high accuracy. And so the answer is actually A. Let's move on. Which piece of equipment would give the most precise delivery of 25 mil of a solution? Again, let's get rid of B and C because they are not volumetric. A syringe, I guess I didn't go over a syringe, but it's not volumetric. And a beaker is not volumetric either. A and D, graduated cylinder and a volumetric pipette. So would a graduated cylinder be more precise or a volumetric pipette? Well, the answer is actually volumetric pipette. Volumetric pipettes have more accuracy than graduated cylinders. And the reason we can't use this particular pipette is because we know that it's a 25 mil volumetric pipette. So that means the marking that it's going to be at is going to be 25 mils, meaning we can use that to deliver 25 mils of a solution. And volumetric pipettes tend to be more accurate than graduated cylinders, and that's why we're choosing a volumetric pipette over a graduated cylinder. So the answer is D. All right, last one. A student wishes to measure 37 mils of a liquid. Which apparatus would be most suitable? Again, let's get rid of the beaker and the Erlenmeyer flask, and we're left with graduated cylinders or volumetric pipette. Remember, a volumetric pipette is going to have, like a single marking, and the 50 mils is not going to help us because you can only estimate when 37 mils of a 50 mil volumetric pipette is going to be filled up. The graduated cylinder, on the other hand, is going to have those markings, and those markings will help you determine when you have reached 37 mils of a certain liquid. So the answer is N. And we are correct. Let's move on to titrations, and thankfully I spelled the header right, like I didn't with volumetric glassware, whatever. So a titration is a commonly used procedure to determine the concentration of a chemical sample. And so if you look at the setup for it, you're going to have a burette. And in the burette is going to be your titrant. And a titrant is going to go into the titrand. And the titrand is usually in a beaker. And in the beaker, it's usually going to contain an indicator. So when you are using a titrant on a titrand, it's usually going to have some reaction. And the indicator tells you when your reaction is complete. Also, another synonym for titrant is a primary standard. So I guess that's just like nice to know, I guess. But basically, when you do end that reaction, that indicator is going to trigger. And a lot of the times, it's going to be like a pink indicator. And that pink indicator triggers when you have completely finished your reaction. And you might notice that this burette has changed in volume. And so that change in volume is really what we look at when we're using a burette to do a titration. And so let's look at this problem. We have a 125 mil hydrochloric solution of unknown concentration, and we're reacting it with 0.1 molar NaOH solution. And so that means in the burette, we're going to put the solution that we know the concentration of, in this case the NaOH, and use that on the titrand, which in this case is 125 mils of hydrochloric acid in this little beaker. And so when that reaction completes, we are going to get that indicator to trigger. And as it turns out, the change in volume that we're going to see is going to be 54 mils. And so now we have to figure out what the concentration of the hydrochloric acid is. Okay, so we know that the reaction here tells us that hydrochloric acid and NaOH are going to react in a 1-to-1 ratio. So that means for every mole of NaOH that we have, we're going to have the same number of moles of hydrochloric acid. So number of moles of NaOH is going to equal number of moles of hydrochloric acid. And so how do we figure out the number of moles of NaOH? Well, we know that we're going to need 54 mils of 0.1 molar NaOH. And so that means we're going to have 0.1 times 0.054 moles. And that is about 0.0054 moles. And since the number of moles of each are going to be the same, that means we're going to have 0.0054 moles of hydrochloric acid. How do we turn this into concentration? Well, we know that this amount of moles is going to be in 125 mils of hydrochloric acid. So remember, concentration is just moles over liters, and 125 mils is 0.125 liters. So that means our concentration of hydrochloric acid is going to be 0.0054 divided by 0.125. And so that means our concentration is 0.0432. Sorry, it's cramped. I always do this, man. I never have enough space. And the answer, yeah, look at that. It's 4.32 times 10 to the negative 2. So in many ways, a titration is stoichiometric. It's going to depend on the chemical reaction that happens, and knowing the amount of volume that has changed, we can determine the moles and relate the number of moles of the solution that we do know to the moles of solution that we don't know. And we can use the moles of the solution that we don't know to find its concentration. The progression of a titration can be shown using a titration curve. And so if we were titrating a weak acid, it would start at like an acidic value, and eventually it'll rise in pH, and eventually it's going to reach something called an equivalence point. And so in that long like vertical thing that you see here, the exact middle is going to be where the equivalence point is. And the equivalence point is when the entire reaction is done and it has finished. And then after that, you're gonna get super basic and just flatten out. For a weak acid, if we look at a weak base, it's gonna be the same except like reverse. You're gonna start off at a pretty high pH, and it's gonna go on. You're gonna have that vertical drop, and at the middle of that vertical drop, you're gonna have something called the equivalence point. And the equivalence point is when the reaction has fully completed. And then eventually, it's gonna go super acidic again. So this entire time, we have been dealing with acid-base titrations. So in acid-base titrations, the species that are involved are acids and bases. And the species undergo a neutralization reaction, and it's usually going to be weak acids and bases that are going to be used as indicators. And acid-base titrations are very common in the industry. But acid-base titrations are not all there is. You can also have redox titrations. And so in order to understand redox titrations, we need to know what an oxidation reduction or redox reaction is. So in a redox reaction, it's a chemical reaction characterized by a transfer of electrons. So let's say we have the equation or the chemical equation of A to B. If there's a transfer of atoms, if B loses an electron and then A gains an electron, that's when we have a redox titration. And so we say that the species that has lost an electron is undergoing oxidation, and the one that gains an electron is undergoing reduction. And so it's kind of weird how they're called reduction if you gain. Well, what happens when you gain an electron is that your charge decreases by 1. And so as you gain more and more electrons, your charge reduces, and so that's why it's called reduction. And it's called oxidation when you lose an electron. So sometimes you might have trouble remembering which one's oxidation and which one's reduction. And there's this really cool acronym called oil rig. So oxidation is loss and reduction is gain. I think this is the best one. There's another one called Leo goes Gur, and I think it's so weird, man. I don't like this one. Basically, it's lose electrons is oxidation, and gain electrons is reduction. Hey, use whatever one works for you, but just know that oxidation is losing electrons, and reduction is gaining electrons. But we run into a little problem. Let's say we have this equation right here, where H2 plus F2 reacts to produce 2HF. How do we know which species is going to be gaining an electron and which one is going to be losing an electron? In order to do that, we look at oxidation numbers. And there are a bunch of rules for oxidation number. So let's use these rules to figure out the oxidation number of this reaction right here. So we have H2 plus F2 produces 2HF. And so first we know that uncombined elements are going to have an oxidation number of 0. So that means H2 plus F2 are going to have oxidation numbers of 0. And you might wonder, there's a 2 here, so are they really uncombined? Yeah, they are, because these are just diatomic elements. You're not going to find them in their monatomic form, so these are uncombined elements. But over here, we have a bit more interesting things. We know that we have H and F. We know that fluorine is always going to be -1. And so that means for any compound, the total net charge must be 0 unless it's like an ion. And so if fluorine is -1, what does hydrogen need to be to create a net charge of 0? Well, hydrogen is going to have to be +1. And so we see for hydrogen has gone from 0 to +1, and fluorine has gone from 0 to -1. So that means hydrogen has lost an electron, and fluorine has gained an electron. And remember, oxidation is lost, so hydrogen is oxidized, and fluorine is reduced. Oxidation is loss, reduction is gain. So hydrogen is oxidized, and fluorine is reduced. This is how you determine in a redox reaction which species is going to gain an electron and which species is going to lose an electron, by looking at the oxidation numbers. And so you might wonder what is an oxidation number. So oxidation number is assuming a non-metal to have ionic characteristics. So we assume that it has like a charge, but again, oxidation numbers are arbitrary. So these don't really exist, but we just have them for simplicity's sake and to help us determine in a redox reaction which species are going to be oxidized and which species are going to be reduced. And so sometimes you get a redox reaction that is not balanced. And depending on whether or not that reaction occurs in acidic, basic, or neutral solution, you have different steps to balance that equation. So first of all, let's take a look at acidic. We are given this reaction and we're told that it's going to happen in an acidic medium. And the steps are right here in order to figure out how to go about the reaction and balance it. So first, we are going to have to split it into half reactions. So in the half reactions, we know that copper is going to turn into copper 2+, and SO4 2- is going to produce SO2. So half reactions is basically just splitting up the reaction into two different reactions that help separate between the redox reaction and then the oxidation reaction. So our next step is to balance elements other than oxygen and hydrogen. Well, in the first one, the coppers are balanced. There's only one copper, everything's balanced. And in the second one, sulfur is also balanced. So we're already done with step 2. So step 3, balance oxygen using H2O. In the first one, we don't even have any oxygen, so we don't need to worry about that. But in the second reaction, we realize that the left side has 2 more oxygens than the right side. And so we can balance that using waters. So we're going to need 2 H2Os to balance out the oxygens, and now the oxygens are balanced. Fourth step, balance hydrogen using H+. Again, the first reaction doesn't even have any hydrogens, so we don't need to balance them. But the second one, we realize that there's going to be 4 hydrogens on the right side, but no hydrogens on the left side. So we can add 4 hydrogen atoms, 4 H+ ions on the left side. 5, balance charge using E-. And so now we can actually make a change to the top equation. The left-hand side is going to have a charge of 0, but the right-hand side has a charge of +2. And so we can balance these by adding 2 electrons. And now the charges are actually balanced. Let's take a look at the next one. We have so we have a +4 charge coming from the hydrogens and a -2 charge coming from this ion right here. So on the left-hand side, we're going to have a +2 charge, and on the right-hand side, we're going to have a 0 charge. And so in order to balance these out, we can add 2 electrons on this side to balance everything out. And so let's move on to step 6. Have the same number of electrons on both half reactions. And so we see that that's already done. We have 2 electrons on the top one and 2 electrons on the bottom one. And so we can move on to the 7th step, which is combine the half reactions. Let me just write the half reactions right here so that's clearer. 2 plus E, 2 plus 2 E minus, and then 2 electrons plus 4 hydrogens plus SO4 2 minus produces SO2 plus 2H2O. And so let's combine these. If we combine them, we're going to get copper plus 2 electrons plus 4 hydrogens plus SO4 2 minus produces copper 2 plus 2 electrons, and then SO2 plus 2H2O. Basically, when you combine, you take all the reactants and you put them on one side, and you take all the products and you put them on the other side. And so now what can we do? Well, we know that there's 2 electrons on both sides. We have 2 electrons here and 2 electrons here, so we can cancel them out. And that was the purpose of step 6. So if you didn't have the same number of electrons, you would still have electrons on a certain side of the reaction, but since we have the same number of electrons on both sides of the reaction, we can now cancel them out. So our final equation, our final balanced equation is going to be copper plus 4H plus SO4 2 minus produces copper 2 plus, oh god, it's going to be so crammed, SO2 plus 2H2O. And that is how to balance a redox reaction in an acidic medium. Now that we've learned how to balance a redox reaction in an acidic solution, let's learn how to balance it in basic solutions. So our first step is to balance in acidic solutions. So our first step would be to split into half reactions, 4, and then ClO minus produces Cl minus. And next step is to balance out the non-oxygen and the non-hydrogen atoms. So let's add a 2 here to balance out the nitrogens on both sides. And then the chlorines here are already balanced. So we're good on that. Next step, adding waters to balance out the oxygens. On the top, the oxygens are already balanced because there are none. But on the bottom, you see that there's 1 oxygen on the left side, but none on the right side. So let's add a hydrogen here, or a water here, And now the oxygens are balanced. Now let's balance the hydrogens using H plus ions. So on the top, you have 6 hydrogens, but on the right, you only have 4. So let's add 2 H plus ions to balance that out. And then on the bottom here, you have two hydrogens from the water on the right, but none on the left. So let's add 2 hydrogens here as well. Next step is to balance out the charges using electrons. So the charge on the left-hand side here is 0, but the charge on the right-hand side is going to be +2. And so in order to balance that out, let's add 2 electrons on the right-hand side. And then for the bottom one here, we have a charge of +1 on the left-hand side, but a charge of -1 on the right-hand side. So let's add 2 electrons to balance that out. And now our next step is to since the number of electrons on both of the half equations are the same, let's now write out the 2 half reactions in clearer here, so that so it's easier to combine. So we have 2 NH3 produces N2H4 plus 2H plus 2 electrons. And then we're going to have 2 electrons plus 2H plus ClO minus produces Cl minus plus H2O. Okay. We know that we're going to have to cancel out the electrons, and so we can just do that here before combining them. And now we can take this and we can combine it. Okay, so I combined it on the next slide here. Let me just move that down so you can see it. And so our next step is to add OHs on both sides to cancel out the hydrogens. So on the right-hand side, we have two hydrogens here. And so let's add two OHs to balance that out. And then on the right-hand side, let's add two OHs here too to balance out those two hydrogens. And what's going to happen is that the H plus ions are going to react with the OH minus ions to produce water. So let's show that really quickly. So 2NH3, I have written this equation a lot of times, plus ClO minus produce N2H4 plus 2H2O plus Cl plus H2O. That's a lot, man. Okay, our next step, sorry, that should be a 2 here. So our next step here is to cancel out waters if possible. That's step 3. Or that's step 4, my bad. So now we can cancel out the waters. We have 2 waters on this side and 2 waters on that side. So we can cancel it out, and we are left with our final equation. 2NH3 plus ClO minus produce N2H4 plus Cl minus plus H2O. And that is how you balance it in a basic solution. So again, very similar to acidic, but in this case, in acidic solutions, you can't have hydrogen atoms just being, liberated. So you need to cancel them out using OH minus ions. All right, so we have one more type. We have neutral. And neutral are very similar to acidic solutions. So when you balance them in an acidic solution, something cool happens. So let's just do that really quickly. We have CO2 producing CO, and then NH2OH produces N2. So first, balance out the non-oxygen and the non-hydrogen ones. The top one is already balanced, and then we just added 2 here to balance out the nitrogens. Second step, balance oxygens. So let's add a water here to balance out the oxygens, and then we have 2 oxygens on this side, so let's add 2 waters on this side. Next step, balance out the hydrogens. We have 2 hydrogens on the right-hand side for the first equation, so let's add 2H plus on the left-hand side. And then on this one, we have 4 plus 2, so 4 plus 2 is 6. We have 6 on the left and 4 on the right, so let's add 2 more here. And now we have to balance out the charges. And so we have a +2 charge on the left-hand side and a 0 charge on this side. So let's add 2 electrons here. And then on the bottom one, we have a 0 charge here, but a +2 charge here. So let's add 2 electrons here. And so now let's write out the 2 half reactions over here. Plus 2H plus CO2 produces CO plus H2O. And then 2NH2OH produces N2 plus 2H2O plus 2H plus 2E minus. And so now we can cancel out the electrons. And the interesting part here is that these also cancel out. And so since the hydrogens cancel out, we can just combine them and we will get the final equation. So CO2 plus 2NH2OH produces CO plus N2 plus 3 waters. There we go. So again, you just balance an acidic solution and the hydrogens cancel out. So neutral solutions are actually pretty easy to do as long as you know how to balance under acidic solution. All right, now that we have a background in redox reactions, let's take a look at what a redox titration is. And so redox titration is a method of determining concentration by causing a redox reaction between the titrant and the titrand. And so it's very similar to an acid-base reaction, acid-base titration, except in an acid-base titration, you have a neutralization reaction that occurs, but in a redox titration, you have a redox reaction that occurs. And I was going to put a problem here, but honestly, it's like kind of big, and this recording is already big as is. And usually they don't ask you to do actual calculations with it. So I'm just trying to get the main ideas down. So in a redox titration, they take place among redox species. So redox reactions occur. And so some redox species are going to act as self-indicators. An example being MnO4-, But most of the times there are special redox indicators. So how in acid-base titrations you have certain indicators, in redox titrations you're going to have some different indicators that are usually used. And redox titrations are most frequent with D block elements. And this is the D block element. It's a part of the periodic table. And the redox reactions that you're going to find are going to usually be here. All right, let's take a look at some practice problems about this whole topic, I guess. Which methods can be used to determine the concentration of HNO3 in an aqueous solution of nitric acid? Okay, so the first is titration with a standard base. And so that does make sense to me because HNO3 is a strong acid. And so if you were to have a strong base or a base in general to do a titration with, that would work. And so A could definitely work. 2, I'm not sure. Titration with a standard oxidizing agent. HNO3 is not, they don't have those D block elements, so likely you're not going to have a redox titration occurring. So 2 cannot be it. And then precipitation with Ag+, we can even try that out. HNO3. What you're going to produce is H2 plus AgNO3. And AgNO3 is not going to be a precipitate. It's going to be aqueous. And H2, of course, is a gas. So precipitation will not occur. And you cannot determine the concentration with precipitation because it doesn't even happen. So the only answer that makes sense is going to be 1. And that is the answer. Let's move on to the next question. The molar mass of a solid carboxylic acid is determined by titrating a known mass of the acid with a standardized solution of NaOH to a phenolphthalein endpoint. Which errors will lead to a molar mass that is smaller than the actual molar mass? Phenolphthalein, by the way, is just like a really common indicator. It's the one that turns pink when you reach the endpoint. And so recall what happens in a titration. So in a titration, NaOH is going to drip into the carboxylic acid, which I'm going to write as Ca. So which of the errors is going to lead to a molar mass that is smaller than the actual molar mass? Well, the molar mass will be smaller if we add too much NaOH. If we add too much NaOH, then it's going to show that it takes more NaOH to neutralize the carboxylic acid than it actually does. And that's going to lead to a molar mass that is smaller. So let's take a look at the answer choices. One sum of the acid is spilled when being transferred into the titration flask. This would not lead to a smaller molar mass. This would actually increase the molar mass because it shows you need less NaOH to get the same amount. And so this is the complete opposite of what we need. So by default, it has to be 2, but let's take a look at what that says. The endpoint is recorded when the solution is dark red in color rather than light pink. So in phenolphthalein, you are supposed to record the endpoint when it turns a light pink. But if the solution is dark red, then that means you have added a lot more NaOH than you are supposed to. So if you recorded when a lot of NaOH is added rather than when the perfect amount is added, then you are going to get a molar mass that is smaller. And so it has to be 2 because it's the only one that makes sense. And the answer is 2 only. Next one, which titration would not require the addition of an indicator? So remember, acid-base titrations are going to require an indicator, but the ones that do not are going to be your redox reactions. Some redox reactions, especially the one with the MnO4 ion in it, are not going to require an indicator. So which answer choice shows this the best? A, determination of oxalate ion by titration with permanganate ion in acidic solution. Yes, this makes sense. The permanganate ion kind of just gives away that it's going to be a self-indicator. So A is definitely a possibility. B, the determination of chloride ion by titration with silver ion. That doesn't make sense. Acetic acid by titration of sodium hydroxide. That's a acid-base titration. And then determination of ammonia by titration with hydrochloric acid. Same thing as C. And so the only thing that makes sense is going to be A. And that is the answer. We have one more question. A dilute solution of sulfuric acid is titrated into a solution of barium hydroxide, and the conductivity of the solution is measured as a function of the added volume of sulfuric acid. Which graph represents the results of this experiment? So let's draw what this looks like. So we have a titration of barium hydroxide, and that's going into a solution of sulfuric acid, HSO4, H2SO4. And so remember, sulfuric acid is a strong acid. And so it's going to be in ions. And when they are in ions, you have to remember that when they are in ions, you have to remember that the conductivity is high because it's going to allow for free flow of ions. So this tells us that the solution is going to start off at a high conductivity. And so we can cancel out A, we can cancel out C, and we're left with B and D. It's going to start high, but what's going to happen is that when the BaOH reacts with the H2SO4, it's going to neutralize it, meaning it's no longer going to be in the form of ions. However, it's going to reach a point where all the barium hydroxide has reacted with the H2SO4. And so after that point, the barium hydroxide goes into this container, but remember, barium hydroxide is a strong base, so it's going to dissociate into Ba plus and then OH minus, and that's going to work to increase the conductivity again. So those free-flowing ions are going to increase the conductivity after all the neutralization reactions have occurred. And so B wouldn't make sense. B would be as if barium hydroxide didn't dissociate into ions, but D does make sense. So again, the H2SO4 is in different ionic forms, and that allows for the free flowing of electrons, meaning the conductivity is high. And then the barium hydroxide comes, neutralizes it, so there's less conductivity. But then after all the neutralization has completed, the barium hydroxide goes in and it splits up into ions, and that works to raise the conductivity again. And so the answer is D, and that is the right answer. All right, that's all I have for this lesson. I hope you learned something, and I hope you'll join me for part 5. We're going to do a bit of practice concerning this entire unit.